tell us about reconstructing space-time from above?
As Sarah says, today I'm specifically going to talk about space-time reconstruction from a non-relativistic boundary. So this work is work with Jim Liu and his student Gene O'Neill at the University of Michigan. It'll be based primarily on a paper that we put out last August, but I'll say a few words about a paper that we're hoping to put out very soon. I've been saying that for a little while, and I was just making plots for it, so I think we really are almost done with that paper. It should be out hopefully in the next week or two. I had to pick only one topic to talk about because I'm only one person and can only manage to talk about one thing, but as Sarah mentioned, I'll be here a few more days, so if you're interested in hearing about some very different things I'm working on, you can ask me about that. For now, let's go ahead and concentrate on this topic. So the idea here is that after the advent of ADS-CFT, people tried to apply this matching between boundary field theories and space-time gravities to other situations besides the conformal field theories that are the CFT and ADS-CFT. And one of the questions that people asked in the original ADS-CFT setup is, we know that we can take information from the bulk and get out information on the boundary, but how does the process work in reverse? If we know what's going on in the boundary, how do we use that to reconstruct what the metric would be, what field profiles you might have in the bulk, etc. And the question that we were asking here is, how does this process work when you're, instead of applying pure ADS-C, you're applying ADS to some system that has a different symmetry. So we might imagine having a non-relativistic scaling symmetry in the dual setup. So, for example, a very popular one to consider is the so-called Licious symmetry, and that's what I've written down here, where we allow time to scale by a factor of lambda to the z, while space only scales with one factor of lambda. So the idea here is that time and space are scaling in some different way as I change the radial scaling. So transverse Lorentz symmetry, that is symmetry along an R slice, has been broken. Time and space scale differently in that given slice. And the question is, okay, so I take one of these space-time setups. I am going to build some boundary on that space-time, and the boundary is supposed to represent a field theory that has this scaling symmetry. Okay, that direction seems all right, but can I go the other way? Can I start with this field theory, with this scaling symmetry, and use that field theory information to rebuild the bulk? And the answer turns out to be interesting, of course, otherwise I wouldn't be giving you a talk. In some ways you can, in some ways you can't. So one particular way that you might be interested in extracting bulk information, starting from this boundary data is a thing called the smearing function. Basically what the smearing function is going to do is take a field profile, so this is essentially a classical field theory. You take a classical field profile on the boundary, use it as some kernel to integrate up and figure out what the field profile is throughout the bulk. So that's the process we're going to talk about today. Just to get some intuition about why we might expect that things work a little bit differently in these non-relativistic dual spacetimes, let's look at the basic Licious geometry. This is the one that I'll be talking about most today, although I'll make a few comments at the end about some other setups, including the Schrodinger geometries. So we can first of all tell that this does obey the symmetry that I said on the page before. If I scale x by a factor of lambda, r by a factor of lambda, in order to keep the thing constant, I'm also going to need to scale t by a factor of lambda to the z, because of the extra power up there. Of course, if I set z back to 1, I get regular ADS and point array coordinates, but we're going to be interested in cases today where z is greater than 1. And there's a weird behavior of light rays in this space-time. So we can use light rays to kind of give ourselves a bit of intuition about how information might be moving through the space-time. When we consider light rays, we find that they run into a potential of this format here. And so they never actually completely reach the boundary.
So the wave will be reflected back to the interior?
Well, yes, but they get reflected back to the interior before they actually hit the boundary. So in ADS, you can get all the way out to r equals to, in these coordinates, the boundary is living at r equals to 0. In ADS, you can get all the way out to r equals to 0 before you have to bounce back. Here, the larger you make the momentum in the x direction, the less close to the boundary you can get before you have to turn around. So you reach some sort of, in the ADS case, that's this black line that I've drawn down here, that's what the potential looks like. You just go straight to the boundary, you hit the boundary and you come back. Yes, you do that in finite time, but you do actually manage to reach the boundary. So you can imagine that information that's living in the center of your space-time does actually propagate all the way out to infinity. Whereas for all of these Licious spacetimes, here I've graphed the potential for 2, z equals 2, z equals 3, and z equals 4 for, I chose some value of p. You end up, no matter what energy you send in, if you have some non-zero transverse momentum, you end up having to have that light ray turn around before it hits the boundary. So you might imagine that, at least just in terms of causal regions, you might think that the causal region is somehow different here. The information that I have here can't actually get all the way out.
I think I have to put a UV color or IR color in the bar.
Okay, so we'll talk about various different cutoffs you can put on the space-time and how they affect this later. So one thing you might actually expect, what people actually normally do when they work on these space-times, by the way, is they'll cut themselves off, rather than considering boundary at r equals to 0, they'll cut themselves off at some r equals to epsilon. But of course, for any epsilon that I pick, if I just make the transverse momentum of the modes I'm considering bigger, then I will still turn around before that epsilon. So that actually won't end up helping this particular problem. We'll talk about IR cutoffs a little later. Okay, but this is really just a geometric optics limit, and maybe we shouldn't trust it. Let's go ahead and see a few more pictures, though. Whoops, oh, I pressed the wrong button. I didn't know I was going to do that. Sorry about that. It's warned and it still happened. Okay. Yeah, so this is just another picture here showing you the causal past of this particular point in the space-time. So this is the point at t equals to 0, x equals to 0, and r equals to 1/2. So I'm a little bit in from the boundary here. And I've drawn all of the light rays that come from the past and go through this point. And this is just two different perspectives on the same thing. So you can see that the light rays that are going to hit this point here, most of them have turned around. In fact, the only one that came directly from the boundary is this one single line right there that has 0 transverse momentum. So the boundary is only providing a little bit, you might guess, a little bit of the information that goes into figuring out what that point should be. And otherwise, the information seems to, like it might have to come from somewhere else. And if I just move this point closer in, all I do is scale this picture and it looks a little bit different, but I get the same situation. There's always only that one single light ray that comes directly with 0 transverse momentum actually hits. So this is just geometric optics. Let's see if we can go a little further. In order to do this, what we're actually going to do is basically classical wave functions. So I'm going to consider the Klein-Gordon equation. That's what I've got up here. And I'm going to rewrite it a little bit. It is easy to rewrite using this particular parameterization as an effective Schrodinger equation, which is nice because then it's easy to analyze by our quantum mechanics intuition. So we'll go ahead and do that. We get a potential that has the following format. I've now restricted to z equal to 2, by the way, for a couple of reasons. First of all, it happens that the z equal to 2 Klein-Gordon equation is analytically solvable, so I can draw you nice pictures and I don't have to work hard, but the same things will hold true for other general z above 1. In other words, anytime that I've broken the scaling between time and space, I've introduced some factor bigger than 1 between the two, then you'll find that I have one piece. This piece looks a lot like the same thing in ADS. This is just going to contribute to a polynomial scaling, and then I have a piece here that's going to be a little bit more problematic, and that's the one we'll spend most of our time talking about. By the way, I chose particular coordinates here. This r is actually, this rho is actually r squared. That's just to make this equation look nice, basically to get rid of the single derivative term. So let's go ahead and compare the situation we know, ADS, to the new situation of Licious. In Licious for z equal to 2, we have a potential that looks really similar to ADS. The main difference is that rather than having just a constant piece dependent on the transverse momentum, we have a piece that goes like 1 over the radius dependent on the transverse momentum. Why does this matter? Well, first of all, the piece that is the same, this piece here, in both cases, that's just going to give us the polynomial fall off near the boundary. That's going to give us the delta plus and delta minus modes that we're used to. The conformal dimensions, these delta plus and delta minus, do actually depend on z. But they're still polynomial fall off, so nothing too strange there. In both cases, we get that as you go very far off into the IR, in other words, you go to very large R, you get to some constant. But for ADS, we have sort of a lower limit on the energy that we can have. So there's no mode available in the far IR when I try to consider energies less than the transverse momentum squared. I can't make an oscillating mode like that in ADS. Whereas in Licious, I can go all the way down to 0 here and still make a mode. Basically because if I just go far enough out this way, the energy will be above the potential. But of course, in both cases, we're still going to get the basically oscillating modes over here because we've got a constant, if we go out far enough, we've got a constant potential, and we've got some energy above it, so what do you get? You get an oscillating mode. And that's the behavior that I've written down here. And this dotted line, by the way, is supposed to represent the modes below this are not available in ADS because that's what the ADS potential goes out to. So energies below this, you can't produce anything in ADS. But in Licious, with that energy, you can. And those modes turn out to be the modes that'll give us some trouble. So this 1 over radius term here, it represents a wide barrier. And by wide, I mean it represents a thing that modes like this have to tunnel through before they get to the region that's dominated by 1 over r squared, before they get to the part that behaves polynomially in the solutions. So this extra tunneling is going to be the thing that causes us problems. It's going to cause exponential suppression of the size of our functions here, depending on what we started with over here. So the game here is basically we're going to be looking at calculating the Green's function. I realize I didn't actually write this up for you guys. Apologies for that. I forget actually which thing I want to set to 0, sorry. So on the previous page, I have here I'm going to assume that near the boundary, I'm just going to call the coefficient that goes like delta minus is A, capital A, a coefficient that goes like delta plus is capital B. The usual way of calculating Green's function in ADS CFT is to say I'm interested in B over A, and then I need to know what sort of boundary conditions I started here. What those boundary conditions tell us is whether or not I have, say, the advanced or the retarded Green's function. So if I ask to have totally ingoing boundary conditions, I believe that's this guy, I turn this piece off, I have just this piece left, and I ask, okay, now propagate this over here, how much of capital B versus capital A did I have? And the answer that gives us the Green's function is this object here. So we're generally going to be interested in things like what the size of these guys are compared to the size of what we started with. And it'll turn out that both of these coefficients are going to be very small compared to the size of what we started here. So if I start with the size of a mode that, let's just call the amplitude of it 1, and then I ask what happens when I let it go all the way over here, it's going to have to tunnel for these modes that are not allowed in ADS but are allowed in Licious. It's going to have to tunnel through this broad barrier, which means it gets suppressed. How strong is the suppression? It's exponential. Yeah.
Do you have a feel for what ADS 2 plus R2 will do if you have that in the IR? So that's Z going to infinity limit of your that wave function.
So I think what ends up happening, let me see if I can remember.
So those exponentials are
Yeah, I believe what ends up happening is that you're going to get a different effective nu here because this nu is set by the dimension. And essentially what you're going to get is the dimension, rather than being the full dimension of your space-time, it'll just be the 2 that's set for ADS2. So I don't think the limit's actually easy to extract from the rest of what I wrote. But essentially what you get is if you have something like you're going to go to an ADS2 region down here, is you'll get a different flat result.
But it will be.
It will end up looking like a constant. Yeah. The behavior will look more like ADS, but the polynomial powers will be different if you do ADS2 plus RT. Yeah.
So are you saying if the wave function, the solutions to the Schrodinger equation will have exponential follow at small rho? But isn't the behavior around rho equals 0 just determined by the line number squared term?
That's right. This piece is polynomial. This piece is exponentially suppressed. It's the size of these guys that's going to be small.
Small in what?
Small in what? Good question. Small in the transverse momentum, in this case it's transverse momentum squared divided by the frequency. And I'll show you that, the exact quantity for that in a moment. Okay. So it turns out for z equal to 2, we can solve this exactly. I'm actually going to look at something a little bit different than the Green's function right now. I'm going to look at the size of this coefficient that is telling me my leading polynomial fall off versus the size of the mode that I started with over here. And you can work out what the connection formulae are between the polynomial behavior here and the exponential behavior here exactly in z equal to 2, so we did that. Here I've built this quantity alpha here. This alpha is the transverse momentum squared divided by, I've called it the energy, but I mean the frequency. It's omega.
Is the scalar mode normalizable in the Schrodinger mode? I mean, is action finite?
In the Schrodinger case?
Yes.
This is actually the Licious case, so it's a little.
Oh, sorry.
It's a little bit, yeah, it's a little bit different.
Because to obtain this green function, you
Right.
need to vary the action of the scalar.
Well, we're actually not going to look at the Green's function just yet. We're going to look at the Green's function at the end of the talk. I just wanted to point that out for the future. At the moment, all I'm saying is I'm not looking at actually normalizing by integrating and setting to 1 a square of the function over the whole range, because that isn't generally going to be normalizable. What I'm looking at doing is setting the size of the mode that I start with here, and I'm going to define that as my normalization. And I'm just going to start with the mode there, and that's why there's this factor of little b. That's the size of the mode that I started with over here. And then I'm going to ask, given the size of that, because it's just some overall constant that a normalization factor would be, given the size of that, what's the size of this guy? And what we find is if I choose small transverse momentum, then they're related to each other by some constant dependent on the mass of the field that you're considering. Nu, remember, is dependent upon the mass. But if instead I consider a limit of this where I'm taking large p for fixed e, in other words, that's a large alpha limit of this equation, I find that I'm suppressed exponentially in alpha here. So the size of this coefficient, capital B, compared to the little one, little b, is suppressed when I've got large p squared compared to e. So how is it that this provides us with some difficulty? Why is this exponential suppression providing a difficulty? Well, just intuitively, before we actually start in the mathematics of it, if I'm trying to look from the boundary and reconstruct what's going on in there, and some pieces of what I know on the boundary are exponentially suppressed, then it's going to be more difficult to try to reconstruct what's going on in the actual space-time. If I give you full data here, you're going to have to work exponentially harder to be able to build what goes on in the space-time. So the precise definition of this varying function that we're going to use, I've given here. The idea is that you start with some boundary information. So I give you the profile of my field at the r equals to 0 boundary. and then I'm interested in reconstructing what the field looks like at every point in spacetime. In order to do this, in order to find what the kernel is that I would need, that's the smearing function is this kernel, normally what you'd do is just expand in Fourier modes and invert to actually compute k. I do want to point out here that this is a relationship among normalizable modes, so I'm interested in the piece that goes like delta minus near the boundary. I'm not asking about the mode that's non-normalizable near the boundary. So the normal bulk to boundary propagator that you're interested in would care about that non-normalizable mode. It in general will not be exponentially suppressed. It's the normalizable mode that looks exponentially suppressed. So I'm taking here normalizable boundary data and turning it into a profile in the bulk. Okay, so I can expand this in Fourier modes and then just invert the transform and compute what k should be. Now it turns out when you're trying to do the inverse Fourier transform here, that isn't defined if you have some exponential suppression. So it isn't defined for Licious spacetimes. The physical way to think about this is we integrate to very large p, which you're going to have to do when you're doing this reverse Fourier transform. When you integrate to very large p, the wide barrier is becoming infinitely insurmountable. And it's hiding some information about the IR from the UV. Specifically, it's hiding the p equals to infinity limit information. For any finite p, yeah, it's exponentially suppressed, but it's just small. It's not gone. But if you were doing something where you actually need to take the limit all the way to p equals to infinity, like this Fourier transform, it falls off too fast. And you can't mathematically define this guy. So when we say, I think in the paper we say something like the smearing function doesn't exist, what we mean by doesn't exist is, I mean, I can't do this inverse Fourier transform. I can't find this kernel k for general boundary data.
Is that because you do not consider the non-normalizable mode?
I mean, the game here is that you're trying to reconstruct space-time profile knowing only you're assuming that you have only normalizable boundary behavior. So in the ADS case, it works just fine. You don't actually have this kind of difficulty because the fall off everywhere in ADS, the only behavior you have is this polynomial behavior. And polynomial behavior is fine for constructing a Fourier transform. It's only the exponential suppression that causes you a problem. So it actually turns out that it's for the same reason that we had those light rays turning around in space-time. It's the same term in the effective potential that shows up that makes those light rays turn around and also causes this tunneling barrier, which makes us have a problem doing this smearing function reconstruction.
I guess I'm a little confused about which part is not well-defined. I mean, I can Fourier transform any outline function.
You can, as long as your the function has to actually be in the proper norm, and it isn't, because the exponential suppression is too great. I think I can come back to that point of better in a couple transparencies, but do bring it up again. Okay, so we might consider some ways to try to fix this problem. The first mention that I kind of mentioned a little bit before, since what most people do is actually cut off at some small epsilon rather than actually taking the boundary at 0, you might think, okay, well, what if I try doing that? What if I try changing what's going on at the boundary, either cut off at some distance inside, or let's even just sew on an ADS region, because I know how to do this in ADS, so maybe if I just fix this pathology at the boundary with the light rays not getting out, then it'll suddenly be okay. But this isn't actually going to help us as far as constructing this kernel, this smearing function goes. You can show via WKB approximation that for any fixed energy, as long as you have some region that's Licious-like, you can set that transverse momentum large enough to cause suppression, and you still can't actually do the reverse transform. You're still going to have the same problem. Someone, I don't remember who mentioned before, that you might imagine changing the infrared region. So I didn't mention this earlier, but when people started to get interested in doing ADS CFT with these other kinds of spacetimes, one of the things that was quickly noticed about Licious is there's a tidal singularity at r equals to infinity. The metric I wrote up before is pathological there. So you might think, oh, well that region is just poorly behaved, so let's get rid of it. Let's cut it out and put in something else, and then this problem will go away. That doesn't help either. So I've kind of given you a bit of a sketch here. By free modes, I mean modes that basically only see the polynomial behavior at the boundary, where the coefficients are not going to be suppressed. So these are modes of high energy relative to the potential, so that the only potential they see is the 1 over r squared. And by trapped modes, I mean things that feel the 1 over r part of the potential and are going to be suppressed. So if I deform the geometry in the IR, I can basically introduce some kind of cutoff on these trapped modes, but there's still going to be a wedge that's a problem. There's always some range where I can take P to infinity, take this transverse momentum to infinity, and I have a difficulty. Another way to see this, I had the plot before of the ADS, and I'm not quite sure what it looked like exactly, and the Licious behavior. Oh, sorry, I got it backwards. This is ADS, this is Licious. And the problematic modes were the modes that lived in here. So if I change what's going on in the IR, all that I do is, say, cut this off at a different place. I can tune the size of this barrier, how big this is, by tuning the transverse momentum. So if I just make the transverse momentum bigger, I'm still going to have some set of modes that have a problem. And these are the modes that are going to live in here.
Good question.
Yeah.
In the first case there, when you do the UV cutoff, doesn't that restrict your momentum that you're allowed to go? That you can't take the transverse momentum to infinity anymore once you do this epsilon?
I don't see why.
Because you now are cutting off.
But that doesn't cut off your transverse momentum.
Okay. Because
It's going to
acting as a UV scale.
Right, it's going to change what you can
Cutoff.
do with E,
Okay.
but it's not going to change what you can do with the transverse momentum. So basically the question there is how much of your momentum are you going to put in transverse modes versus radial?
Yeah.
And you're changing the ratio, and it's changing that ratio. That's the problem.
I'm confused, because I would think that you can't, I would think that the momentum always has to be below whatever scale you have in the problem. So in this case, if you go above that scale, you're affected as regional breakdown. So what?
So you're actually hitting on what I'm about to get to, so let me get there.
So I guess I would
Yeah,
agree
okay.
with what points.
I'll get there, about a transparency and a half.
Okay.
Yeah, okay. So before we discuss, I think you guys are getting on the probe limit here is going to be poor at some point. But we'll discuss that in a second. So first of all, let me talk about what happens. Okay, fixing the boundary doesn't seem to fix the problem. At least just mathematically, if I just assume that all I have is Klein-Gordon in this background, I'm not going to worry about back reaction or anything else. If I do that, then fixing the boundary doesn't help, fixing the IR doesn't help, fixing both also doesn't help. So Jim and Gino have a set of numerical solutions, then we went ahead and just used their numerical case. There's been a bunch of other work on these spacetimes where you patch up the Licious by adding something to the UV and something to the IR. We just used this particular one because they had it numerically. So even if we choose bulk points within a fixed region, so for example here this is a picture of trying to do the integration to create this kernel for some point in the ADS4 region. So what I'm talking about here is when we define this mirroring function, I'm finding it for a particular location. So I'm trying to say, I'm interested in this particular point in the space-time. Now tell me what the full profile is on the boundary. You're going to have to do some particular integral to get out what's going on right here. And if you choose right here instead, your function looks different. It's a function of both what radius you're at as well as what time and space you're looking at the block.
How do you know what the back reaction contributes to this problem? When you say just
That's what we are just assuming that it doesn't do anything. This is just classical wave mechanics in the background.
you
That's
say
it.
just it's a smaller effect.
The
That's it.
We're assuming that it's a small effect at the moment. As these guys pointed out, it will actually end up mattering, but that isn't something we've considered in full detail yet. Okay, so getting back to these pictures here, so what's going on here is this is trying to build K for a point in the ADS4 region, and the yellow gradient here is modes that are problematic, and you can see that they're still present. And as you integrate up towards infinity, you are still going to run into them if you allow the transverse momentum to get arbitrarily large. This is the same picture. You can see it. Yes.
I'm sorry.
Yeah.
So I'm not allowed, am I allowed to think of this as deep IR modes or not?
To think of which, sorry.
The modes that, these modes that are problematic, can I think of them as living deep in the bulk, or?
I think you do want to think of them as living deep in the bulk, because the modes that are becoming problematic are modes that start off with a large behavior in the bulk and then are very suppressed at the boundary. So the other way to say this is that if I started out with a size 1 over here, they blow up very large as I try to go in.
Okay, then, well, all right, I'll come back later to that.
Okay.
You require the modes to be regular and in the origin of geometry.
No, we're not. We're assuming that they're inflowing or outgoing in the IR region. So we're assuming that they oscillate like, rho minus t or rho plus t in the IR.
So your IR have another horizon, or?
Well, actually, right now we did add another horizon, but the first case we considered was just pure Licious. We're not thinking about there being a horizon. We're ignoring that there might be a pathology in the middle of the Licious spacetime, which there is. And we're not considering back reaction issues. Just as a first pass to see what happens. Basically, the way that this started is we first knew about the geometric optics problem because that had been discussed much, I think it actually maybe was even in the original paper on Licious, but long before we thought about it. And then we wanted to know, does the same thing show up in the classical wave picture where I just have the space-time background and I'm solving the Klein-Gordon equation on top of it? And so we started with the simplest process for that. Then we were asking, okay, well, what happens? So that has a pathology, but then what happens if you try to fix it up? Fix the boundary, fix the IR, fix both, and it still hasn't helped. But what does work is if you institute a strict cutoff on P. So if you say, I'm going to consider on the boundary only information on the boundary that has up to a fixed momentum. If I do that, then it's fine. Then I can define the Fourier transform. Basically here the idea is that I'm defining something with compact support on the boundary in P space. And so if you have compact support, you can always define what the Fourier transform is. But if you consider general functions, it turns out you won't be able to. Okay, so yes, this does work. And as you guys pointed out, there actually are some physics reasons why you might want to imagine starting with a strict P cutoff. The first, I think, reason that you might consider it is that from the perspective of what's going on the boundary, we never expected that the spacetime should be the sort of UV completion of the field theories, the non-relativistic field theories that they're dual to. The general idea here is that you're trying to say, I want to apply ADS CFT to some condensed matter problem. And, well, we know what the UV of a condensed matter problem is, and this isn't it. It's some atoms or whatever high order structure you have. So we aren't really surprised that things break down when you ask to consider arbitrarily high P modes. So maybe you just shouldn't. Okay. Another reason to think about it from the perspective of the space-time is that I should be worried about back reaction as I tune up the energy that I'm putting in to my background. And we haven't considered that issue at all. This is looking without that case. The main reason that we still think this is interesting is because in the exact ADS case, you don't need to add any cutoff by hand. In the exact ADS case, everything that I've discussed so far is perfectly well defined, allowing P to go arbitrarily to infinity. Yeah.
As you mentioned, many computations, you really do put in a little epsilon.
The epsilon doesn't
Right.
help you.
Well, it doesn't, but you do that in ADS and Licious and everybody, right?
Mhm.
And I have this naive picture that, okay, in ADS, where you have actually a full Lorentz symmetry, you pick a scale, you're done for everybody, for my direction, for your direction,
Right.
everybody has. But here it seems like because you've broken the symmetry, you get to sort of pick different.
I'm not sure you actually get to pick another scale because you still know the scaling between the space and time. It's just not one.
Well, but if I cut off sort of both in energy and this P,
Mhm.
then it seems like I do know the scaling, but then I can construct a sort of dimensionless parameter by taking the
Sure.
right ratio, and I could ask what happens as I vary that. And
Yeah, I think that's true. I think that's true. And I would even say that the dimensionless parameter you should be constructing is the alpha that we had before, and what you're interested in, where did I put alpha? Yeah, it's back a few pages. What you're interested in is cutting off in this guy
yeah.
here. Yeah. I think that's true.
That's for Z equals 2. So
That's
general
yeah, that's
Z.
specific to Z equal to 2. In general, you have the power on this guy is dependent on Z in some way. But it would always be dimensionless for whatever Z if you compute out correctly. That's the point.
So if Bach geometry has this dilatation symmetry, can you use them to rescale your cutoff such that the cutoff can descend to infinity?
I don't think you'll be able to change alpha though,
So
because I think it's dimensionless. So I think rescaling won't change it.
but your Bach geometry has such symmetry, I think should have some implications in your solutions. If you just cut off from momentum, but not cut off from something else.
Well, I think that it does actually, and I think the way that the implication that it has is that the only quantity that really matters is the ratio of E to P squared. You don't care about E individually or P individually. And I think that's a remnant of that symmetry.
So you put cutoff from P squared over E or?
You can put a cutoff on P squared over E. You can actually effectively also cut this off by putting a strict cutoff at large P. That will work.
That's basically something like a mass scale. Because P squared over E is something like mass in a non-relativistic system.
If you have Z equal to 2. If you have a different Z, it's going to be a different ratio.
In this case,
Yeah. Okay, but it's still the case that there's something different from what we found in ADS. So in ADS, you don't have to worry about adding a cutoff like this by hand. It's just the case that you can take arbitrary data on the boundary and integrate up and get what the field profile should be throughout the spacetime.
But I still could imagine having some modes that are very localized in the bulk.
There is
They don't
actually,
make it to the boundary at all.
you can,
So you
and
wouldn't be able to reconstruct anything from those.
yeah, well, so the case in ADS where that happens is if you have thermal ADS, so you have some black hole, and that's actually, these guys here wrote a fairly recent paper talking about this setup. And what happens in the case where you have thermal ADS, so you've got some black hole, is that indeed there are some localized modes. The modes that are localized there are modes that have a large momentum around the black hole. So large angular momentum around the black hole. And that large angular momentum acts very similarly to our large transverse momentum.
So they can they trace? So there's a similar suppression.
So they're going to have a similar suppression for large omega, if you will, so large angular momentum modes, L, I guess, around the black hole. One of the things that ends up being different for them is that if they're interested only in reconstructing the bulk far away from the black hole, these modes don't cause them problems. For us, because I think maybe because of that dilatation symmetry, maybe that's the way to think about it, because there are modes everywhere that are trapped. They aren't trapped in a physical way, in a physical location. They're trapped because their transverse momentum is too high, and you can build one with a transverse momentum too high anywhere in the space-time. That means everywhere in the space-time you have this problem. Whereas for the ADS case, you really only have the problem locally around somewhere near the horizon. They are localized in the IR there. Okay. Right, so a strict P cutoff is actually going to be okay. So I mentioned that I would spend a little bit of time talking about the paper that we're talking about now. So in addition to these issues about whether or not we're still in the probe limit, there's also a question of everything we did was just one point. We were trying to start with the profile here and compute from one point information what the bulk profile is. But you might expect that something non-local, and the least non-local thing I guess you could do is a two-point function. So let's look at Green's functions, what happens with them. So the idea here is now I'm taking data from 2 points on the boundary and asking, is that enough to be able to reconstruct what's going on in the bulk? And it turns out that the Green's functions actually do have some echoes of the same behavior. So what I've written up for you here now is I've written up the Green's function for ADS, and I'm using a particular scaling, the front piece doesn't matter, where I'm imagining a small change in the boundary condition in the infrared. So once again, the Green's function, normally what you do is you compute the ratio of the normalizable to non-normalizable modes given a certain boundary condition in the infrared. Normally, we're interested in the retarded Green's function, so we usually pick infalling boundary conditions in the infrared. To perfectly know the infalling boundary conditions, I'd have to know the geometry all the way in. So what I'm imagining here is that we screwed up a little bit, and we picked infalling boundary conditions actually with a little bit of outgoing as well. And that's what this epsilon represents here. So I'm doing a small change on the boundary conditions in the infrared and asking, does that change the Green's function? Can I see that in the Green's function at the boundary? And the answer for ADS is yes, of course I can see that. And you can tell that it's visible because the size of this term that depends on the epsilon is of order 1. It's something dependent on nu in some way, but it's not small. Whereas if I try to build the Green's function for Licious equal to 2, once again, we can compute this exactly, so it's nice, but you can show that the same effect happens in a WKB approximation for any C larger than 1. This is the Z equal to 2 case. What I find here is that when I make the transverse momentum large again, like exactly this alpha goes to infinity limit, I find that the behavior at large, the behavior when I make this small change at large alpha is suppressed exponentially. So it's hard for me to see a change made in the boundary conditions in the IR that only affects large P modes. So if I do something to the space-time here, add some ripple that is at large transverse momentum, so only large transverse momentum modes could possibly see it, but then there isn't a good probe to find it from the boundary because information about it, the Green's function probe that we might naively try, ends up being suppressed. And once again, this is going to, this suppression, of course, is set by the size of alpha, so if I have some cutoff on how big I'm letting that be, then I'm also not particularly worried about my ability to reconstruct it. I should have pointed this out, sorry, in particular, the bit of it that's suppressed is the spectral function, it's the imaginary part of G that's suppressed. So I also promised that I'd spend a little bit of time talking about other non-relativistic dual spacetimes. So pretty much everything that I've said today is true for Licious for Z greater than 1. So we have this technical problem producing a snaring function kernel. It doesn't exist unless we put a P cutoff in. And the spectral function has this suppression behavior that it's hard for me to see changes in the boundary conditions in the infrared from the boundary if I'm asking about modes at high transverse momentum. As we talked about before when I said we try to fix the boundary, we try to fix the IR, we try to fix both, this happens for any spacetime that has any Licious-like region and also has a transverse symmetry, as long as the Z in the Licious region is greater than 1. we end up with the exact same problem. So fixing the boundary and fixing the IR doesn't help you. I have not showed here, but it is true, that Schrodinger with z equal to 2 does not have any of these problems. It acts exactly like ADS. The effective potential is exactly the same as ADS, except that the effective nu does depend on the momentum in the null direction. Basically, this is supposed to be, the idea with the Schrodinger spacetime is it's supposed to be a spacetime that's dual to a system that has particle number in it. And the momentum in this extra direction is interpreted as something like the particle number. So the effective conformal dimension that you're going to get, which depends on nu, is going to depend on what that particle number is. But everything's fine. The smearing function is fine because it's just like EDS. And the spectral function has the normal conformal scaling near the edges and looks just like ADS. Nothing's weird there at all. You can also consider Schrodinger spacetimes with a symmetry, so the scaling symmetry somewhere between 1 and 2. So this is where space and time don't scale a full 2 dimensions apart. Space doesn't scale twice time, it scales like 1.5 times time or something. And here what you find is, because we usually work in a fixed particle number, so we're going to work in a super selection sector in this null momentum, because we do that, the smearing function is okay as long as you're going to stick in one of those. This is basically because you're not integrating over the thing that causes exponential suppression. The exponential suppression is set by the momentum in this null direction. You do, however, see that the imaginary part of this Green's function is suppressed. So once again, it is a little hard to see information, so certain kinds of information in the boundary, in the bulk, in the deep IR are hard to see from the boundary. So we haven't looked at this in more detail, but I think we suspect that basically what's going on with this case, the algebra, the symmetry algebra for this Schrodinger has an extra generator. It has a special conformal generator that's not present down here. And we think that that's what's saving us here. That's what's making that okay. That symmetry forces it to everything to work out in a very conformal-like way. So since I have a little bit more time, I'm actually going to escape out of this and show you guys a couple of plots if I can, to give you some more intuition for what I'm talking about with these Green's functions. So I think these ones are the most interesting. So what you're looking at here, is a plot of the Green's functions in 4 different spacetimes where I've fixed the value of nu, so I'm not varying the mass between the different cases, or rather I've set the mass in each case so that nu is the same for all of the pictures. And then you're looking at a contour plot of the spectral function as I vary the, is this direction. As I vary the transverse momentum left and right, and the energy, that's this omega or E scale up and down.
And this is all z equals to Licious?
No, they're different. So the first one you're looking at is ADS. And as you would expect in ADS, there are no modes available for omega less than k. So if I make the energy lower than the transverse momentum, there's no modes available. What does no modes mean in terms of the spectral function? It means it's 0. The imaginary part of the Green's function is 0, where you have no modes available. And that's what we see here. That's this white region that's 0 out here and out here. And then as once I allow omega to be bigger than k, I see that the size, I start to have modes, and I see that the size of it grows as I make that combination bigger. This next picture here is Licious z equal to 2. And what we see here is that it never actually totally goes to 0. Because I can allow the energy to go all the way down to 0, and I still have modes. So it gets small, And it gets, this dashed line is supposed to represent the region where it's exponentially small out here. And then it gets larger as I go into here. But it never actually goes to 0. It never actually goes away. There's always modes available. The size of these modes is very tiny. And so we can imagine, because these modes could be present in the IR, if I'm trying to reconstruct from just the Green's functions data, it's going to be really hard for me to see any changes that happen in this region. That's going to be hard to construct. This is the picture for Schrodinger with z equal to 2. So once again, there's this region where it's just exactly 0 because there are no modes available. So there's no problem. And above that line, it rapidly gets big so that you can see the effect. And this is Schrodinger with z 3/2, which also is exactly solvable. And in this case, we find that there's a region outside of which it's actually 0. Peter has a hard time finding that, but it is true that it's exactly 0 out here. And then there's a little slice where it's exponentially suppressed. And then it behaves just fine. And we can figure out what's going on up above here. The problem region, the region where we have trouble reconstructing the space-time profile from the boundary Green's function information, is right along here. It's in this slice in between. So we can see that the Schrodinger with z between 1 and 2 kind of has some of the behaviors that happen in plain old Schrodinger and some of what happens in the Licious case. But it does still have this sort of suppression region. So it's not something that's entirely related to the pathologies of Licious spacetime. It seems to happen in Schrodinger as well. It is something that seems to be related to when you break transverse Lorentz symmetry. That's when you start to have some tunneling barrier in your effective potential, and that's when you start to have trouble being able to reconstruct your spacetime. And the signal for when this happens is when, going back to the very beginning of the talk, it is when we have some light rays that do not reach the boundary. That's exactly and only the time when we have a problem. Outside of that case, we don't seem to have difficulties.
Have you plotted the poles of retarded Green?
Yes, I have. There aren't any, they're on a different sheet. So that is what's going on above here. This is, I'm actually just plotting the imaginary part here. So there are poles, the branch cuts in the Green's function. This is just the, in the same order, so this is regular ADS. This is Lipschitz equal to 2. It's a little hard to see here, but there's a branch cut that starts at k, plus and minus k, and goes out to infinity. So drawing the picture for this, we have some branch point there. And of course, the EDS one doesn't have any poles, it just has this branch structure, and that's it. For the Lipschitz case here, for z equal to 2, the branch points have come all the way in and hit each other here. This is the retarded Green's function because there's nothing in the upper half plane that's fine. Where the poles are hiding here, I haven't drawn any because they're on another sheet. So to actually get to them, you have to wrap around onto the next sheet, and then you'll actually find that there's a set of poles here and another set of poles down here. Those poles do accumulate, and they do cause this guy to be an essential singularity. That essential singularity is actually the signal that we're having this exponential suppression. It's related to the same thing. And just to go ahead and give you guys the little pictures for these two as well. The Schrodinger case looks very much like half of the EDS case. So it just has a branch cut on one side because it goes like omega instead of omega squared. And this is fine because we expect it to be non-relativistic, so it's not weird to have plus and minus omega being different. And for the Schrodinger with z equal to 3/2, it's a very similar picture, but once again, you can find poles if you go into the next sheet. You just don't see them here. And in that case, this is an accumulation point, and it is an essential singularity. I'm really glad you asked that question, because that's the reason we didn't put this paper out two months ago. Otherwise, it would already be done. Okay, so let me say a few more words about future things that one might want to that one might be interested in looking at. So one can also build up transformation, if you know what the Green's function is at the cutoff surface in the infrared, can you build what the UV Green's function should look like? And that transformation is possible. And if you try to do some numerics with this in a Licious to ADS R2 flow at the boundary, we've done a little bit of numerics about that, and it does show that there's some suppression of what the signal is. So what this is saying is that if I change what's going on in the IR and the Green's function, and then I try to propagate that guy out and ask what the Green's function is at the boundary, changes are suppressed exponentially in this same parameter alpha. We could also ask about considering the probe limit. So a few of you guys brought this up during the talk, that if we insist on considering these very high P modes, we're going to be considering high energy things, and we're outside of the probe limit in some way. And the question is, do we wander outside of the probe limit before we start seeing the suppression effects that cause us problems with building the spheric function, or with seeing changes in the boundary conditions in the Green's function? And we haven't done an exact study of that yet, but we are interested in looking at it. And I believe that's all that I have for you, but let me check. Yes, I think that that's all I have.
If even the consideration of the smear function make you struggle so much, one wonders, is the state of affairs with regard to holography for a non-relativistic boundary in truly bad shape or not? What's your take?
It's not that bad, actually. So I was really
Now,
worried.
why is that?
Well, so I was really worried about it for a while, but there's a couple of reasons why I think you shouldn't be super concerned. The first is that really these problems are all happening at the infinite P limit. The problem with constructing the smearing function happens because I'm not putting some P cutoff in. And for physics reasons, we're not surprised to put a P cutoff in, so maybe that's okay. But possibly the more important reason is what we're mostly actually interested in getting out from the ADS condensed matter kind of picture is we want to do things in the space-time and then ask what that does to the boundary. That's not the direction that's a problem. The thing that we're having difficulty with is the other way. Telling me what's going on in the boundary and building an exact space-time that mirrors it up to arbitrary P, that's where we have difficulty. So you might say, first of all, I don't care about arbitrary P, and second of all, I don't even want to go that direction. I want to go the other way. I want to try to find out what's going on the boundary.
Well, to go the other way, you need to make sure you have the correct model that's supposed to describe it.
Right, but we're not surprised by the correct model probably should have a cutoff in it. So it's not necessarily a terrible thing to have add that. On the other hand, I do think that you should be concerned about things like even just the basic issue with the light race. You might ask, okay, well, where's your boundary? I do think that those are interesting questions if you want to try to take this as an exact duality as opposed to just something that's effective and useful. I think it certainly has been shown to be effective in certain limits. Useful, I think we're still working on, but it could be. This doesn't prevent that being useful. What this prevents is exact mathematics as far as allowing things to go to infinite P limits. And again, I think it's pretty important that we haven't considered this probe limit because it's possible that magically when you consider the probe limit, all of those things which we've talked about today fall outside of that. In fact, it's reasonably likely that that's the case. And there's sort of a natural P cutoff provided by the space-time itself. I can certainly imagine that that might be true.
In the symptotic ADS case, we know there is bound on there is unitarity bound on the mass of scatterers. There is similar bound in Licious or showing.
You do have the similar bound. So the news that I've been showing you are much like the ADS new in that you don't want to let them be below zero, the radical that defines them. Yeah, it's still a lower bound, but that is a different bound on M because the function in terms of M looks a little bit different.
In that case, how do you define how do I say it is unitary? It is unitary. For example, in this case, we know the mode is normalizable.
So well, it is actually still a normalizable versus non-normalizable consideration. Yeah, it's still the same consideration, and you do find actually very similarly to the ADS case where below a certain mass you actually have both choices being normalizable. It turns out that the same thing happens for Licious. For Schrodinger's equal to 2 it doesn't, but for the Licious case the same thing happens where below a certain range you have both boundary conditions available. There is a interesting and sort of weird pathology that happens at the top end of that range. So it looks like the range is a little bigger where you can do both than the ADS case. It looks like Z sets the top of that range, but it turns out between the ADS cutoff to the range where you can pick both and the Licious cutoff to the range where you can pick both, there's another pathology that shows up. This is something that Simon Ross and his postdoc Tomas Andrade found. So yes, it behaves very similarly, but there are a few curious features that are different. And even trying to do holography in these spacetimes, just in terms of, say, you wanted to do holographic renormalization, it looks different. But there has been some work on doing that more successfully in the Licious case, I think, than in the Schrödinger case. That is something I'm thinking about with Simon Ross and his postdoc at this point, but we're still working. Can't say much else.
Are there no more questions? That's Cindy.